So we have the concept of what we call cost insight generate, where we automatically analyze parts for manufacturability and cost. I'm going to show you how we do this in actual fact, but most of the work is done in the background. Most of the work is done on a server somewhere that's doing some very clever stuff. The design engineer, which would be me in this case, I create a design and I send it into my managed environment, into PLM. It gets checked in. And then from there, it takes over. So it then gets simulated for its manufacturing process, and it generates information with cost drivers, manufacturing process steps, resources required, costs and tooling, and so on. That information is then analyzed, and where there is something that's not as good as it should be, there's lots of areas there, it can then post information back into the PLM environment, so we can now join together the design we're working on and the challenges we expect to face on them. And therefore, people can see reports inside there or through email notification on which components require the attention of a design engineer, manufacturing engineer, a cost engineer. And therefore, we only put our valuable resources on the opportunities that we really can exploit. And then we use some of the cost insight tools to understand why, exactly what's going on about these, and then make decisions and change design so we can get to market with the right product. So let's have a little look at how that happens in practice. I'm going to start off with an email. So I've got an email from that exact same system that I just showed that tells me I need to go and do something. And then that's all. I'm spending 99% of my time focusing on designing this product. And then I get an email that says, you need to look at this flywheel here, this part here. As you can see, it has a DFM risk of high, and that's the cost of that component. It's a very small component, only a $2 component, but we're thinking about producing 50,000 of these a year. And if it's not easy to manufacture, that $2 is probably a little bit high. And it's all these little $1, $2 savings that all add up. And of course, we can't focus on every component. So that's the beauty of this email. It's telling me this is the one you should have a look at. So when I click on the URL it provides, it's going to take me to the managed environment where this component exists. This component exists in Windchill. Windchill is the managed environment that we are using in our organization. It's a PLM tool, if you like. And Windchill contains the data about all my parts, all my documents, the processes that are driving through my organization. And this is the flywheel part in itself. If I look at the related data to it as it goes through its life cycle, there's one piece of information that's now been attached. As a result of the simulation being done against that part, again, in the background, without me doing anything, the report summarizes all the problems that we're going to face. Here's the component itself, information about its title, the volumes it's produced in, the costs, and then the manufacturing issues, and there's a whole bunch of them. Now, I could sit and read this list, but there's a smarter way of doing this. I could use the tools that this system is providing me inside a priori to understand what to do next. So also attached to this part, against its information pack, is the actual simulation itself. Now I can get to see why this component is the price that it is. So first of all, I see the physical component itself. This is not CAD software, this is not design software. This is the view of the simulation that was run on my behalf as a design engineer. Now you can immediately see what's kind of going on here. This is a flywheel that sits at the back of my drill. It has two jobs. One is to cool the system, and the second one is to add weight into the flywheel system for inertial perspective to keep the motor running when the clutch is disengaged. So those are the two major functions. It also has to be strong. It also has to resist temperatures, vibrations, and so on. So this is the answer I've come up with. I'm an exhausted engineer. Some might say lazy, but I've designed something which seems to fit the bill. I've put in two enormous weights in here, one of which I've got holes in so I could add balancing weight so that it can be balanced in the secondary process. I also have little ribs, which from an inertial perspective, I made really thin because I want these to just support my counterweights and add a bit of strength. I don't want them to be heavy because I want the weight on the outside to create inertial mass. I also have the cooling fins themselves, which are classic cooling fin designs, nice and thin, allowing air to flow through. However, on the very left-hand side, you can see the information about the simulation. The first thing it tells me is this is the process that it's determined it's going to use to manufacture it. It's got, for example, 31 seconds of high-pressure die casting, followed by a trimming process, and then some milling to do some holes and other machining features based on the tolerances that were applied to this part. It's just worked that out based on some parameters and the CAD model. CAD model's the crux of it, but also it knows which major process group it's going to be manufactured in, where it's going to be manufactured in the world, and volume, batch size, material. All this data has come from the world of PLM. That data exists somewhere in my organization. We've hoovered it up in the background and glued it to the 3D model to allow us to simulate the process. We therefore get the cost and the cost breakdown, including the tooling cost that doesn't produce this for one tool, but many tools that are going to support the life cycle of this part. We're looking at 50,000 components over 8 years. It just worked that all out from the manufacturing simulation